we are about to find the product of a monomial and a binomial. And in fact, we've done this before, and we called it applying the distributive property. We multiply the monomial times each term of the binomial. So we start with 4 times x, and we get 4x, and then 4 times 16, and we get 64. Well, now we're going to find the product of a pair of binomials. The first binomial is x plus 4, and the second one is x plus 16. But we still apply the distributive property. We start with the first term of the first binomial and multiply it times the first term of the second binomial. In this case, x times x. And then that same first term times the second term of the second binomial, x times 16. And now we focus on the second term of the first binomial, 4. Multiply it times the first term of the second binomial, x, to get 4x. And finally, the second term of the first binomial times the second term of the second binomial, in this case 4 times 16. We simplify each term to get x squared plus 16x plus 4x plus 64. Two of the terms are like terms. We combine them, and our final expression is a trinomial, x squared plus 20x plus 64. We started with a pair of binomials. Each binomial, of course, has 2 terms. It's not surprising that 2 terms times 2 terms yields us 4 terms, but in this case, 2 of the 4 terms were like terms, so our final expression had 3 terms. When multiplying 2 binomials, multiply each term of the first binomial by each term of the second binomial, then combine like terms. Well, here's a binomial squared, but it can be rewritten as a product of 2 binomials. The difference, of course, is that they're identical binomials. The rules don't change. A times A times B times A, and B times B. And then the 2 middle terms, one's an AB, one's a BA, but we know because of the commutative property that that's the same thing. So an AB and a BA is like an AB plus another AB, and that simplifies to 2AB. So our final expression is a trinomial again, a squared plus 2ab plus b squared. Here's a line segment, and we're going to use this line segment to visually show what we've just done. We mark off an arbitrary distance with the point as shown, and so our first length we're going to call A, and our second length we're going to call B. So the entire line segment has length A plus B. And then we're going to make a copy of the line segment to form a square where each side of the square has a length of A plus B as shown. So the area of this square can be written as the quantity A plus B squared, because to get the area of a square, it's the length times the width. But of course, the length and the width in a square are the same thing. Then we're going to extend some line segments from the marks we made so that this square is divided into 4 rectangles. 2 of the rectangles, as you can see, are also squares. And the first one, of course, length times width is A times A, or A squared. Then we have a rectangle with length A, width B, A times B. Then another one that's B times A, and the final area is a square at the bottom left, B times B, or B squared. If we add up all those areas, that should give us the area of the whole shape. And here we are. And that's the same expression we had before. The 2 in the middle are like terms. So it's a visual way of showing that the quantity A plus B squared is equal to A squared plus 2AB plus B squared. Now here's an example of a pair of binomials where all the terms are different. So we have A times C, A times D, B times C, and B times D. So in this one, there are no like terms, and that's as far as we can go. We can also do a visual with this one. There's our A plus B, but now we have a new segment that's C plus D with different distances. The first one can be labeled A plus B, the second one C plus D. Now we have a rectangle instead of a square. The length of the rectangle is A plus B, and the width is C plus D. We extend, as we did before, to divide our rectangle into 4 regions. And our first region is C times A, length times width. And the one at the bottom left is D times A. top right C times B, and the bottom right is D times B. We add up all of those terms, CA plus DA plus CB plus DB, more commonly written in alphabetical order, and that's the same expression we had before. Once again, we've shown visually why the binomial A plus B times the binomial C plus D comes out to be AC plus AD plus BC plus BD. Here's a binomial times a trinomial. So we start with the first term of the binomial, and we multiply it times each term of the trinomial. So there's three products here, and we write them down as shown. Then we take the second term of the binomial, the 1, and multiply it times each term of the trinomial. Not so difficult because 1 times anything is itself, but we still perform it and write it down, and we add our two products together. There's 6 terms, but there's 2 that are like terms, and there's 2 more that are also like terms. We combine the like terms, and our 6 terms have combined down to 4 terms, a cubed plus 8a squared plus 19a plus 12. Here's an interesting one. It's a binomial cubed. So let's rewrite it without the exponent. And the way to do this is to do 2 of the factors at a time. And remember, a factor is a thing to be multiplied. So in this case, each binomial n plus 1 is a factor. So I am going to take the second and the third factors and multiply them together, as shown. We've done this before. And then we recopy the first factor, the n plus 1, over on the right. It was there in the middle line, and it's still there in the third line. But in the rest of the third line, we have the results of the second n plus 1 times the third n plus 1. There's some like terms going on there, so we're going to simplify that to get a trinomial. And now we have a binomial times a trinomial. We've done that before. We take the first term, the n, times each term of the trinomial, write those products down. Then we take the second term, the 1, times each term of the trinomial, find those products, write them down, add them all together. We have some like terms. There's 2 of them. There's 2 more. We combine the like terms. We get n cubed plus 3n squared plus 3n plus 1. Here's an interesting type of problem. We have a binomial x minus 3 times another binomial x plus 3. The rules don't change, other than we might want to change the minus 3 to plus negative 3 to avoid making a sign error. So that's what we do. And then we have x times x times 3. Negative 3 times x, negative 3 times 3. We simplify our terms. We get x squared plus 3x plus negative 3x plus negative 9. We have 2 like terms, but we also notice that they are opposites. Opposites add up to 0, so for convenience, we just cross them out. And we're left with x squared plus negative 9, more commonly written x squared minus 9, and this is known as a difference of squares. Here's a mnemonic device, an acronym known as FOIL. First, outside, inside, last. Many mathematics educators don't like using this mnemonic device, but I mention it here because it's so widely used. You probably should recognize it if someone else uses it. I'll just show how it's used when multiplying a pair of binomials. Here's an example. First, in this case, means the n times the n. Outside here means the n times the 4. Inside means the 3 times the n. And last means the 3 times the 4. Sometimes the acronym is used as a verb. Someone will be looking at a pair of binomials that are to be multiplied, and someone might say, well, what should I do? And someone else might help out by saying, you should FOIL those 2. But it's worth noting that it only works for multiplying a pair of binomials. Doesn't work for a binomial times a trinomial or any other type of multiplication of polynomials except for a binomial times a binomial. To summarize, when multiplying 2 binomials, multiply each term of the first binomial by each term of the second binomial, then combine like terms. And since a binomial is a special type of polynomial, we can generalize by stating, when multiplying two polynomials, multiply each term of the first polynomial by each term of the second polynomial, then combine like terms.